So today I'll be presenting Crossed Dipole Antenna near field simulation using Ansys HFSS, and a little bit about my background. I'm an application engineer at DFE-Tech with over 3 years of experience with Ansys certified professional in low frequency and high frequency electronics. And I'm already a certified HRDCOP TDT trainer. So this is the certificate. And for today, upon completion of this webinar, we will be able to learn how to define what is near field and far field radiation, how to simulate near field radiation of line and sphere using Ansys HFSS, and finally we'll be plotting the result, the near field radiation pattern using Ansys HFSS. And before we go to the demonstration, here are some of the Ansys product that we provide. So for today, we will be focusing mainly in electronics. So some of the electronics product is that HFSS. I'll go through this later. And then Maxwell. Maxwell is a electromagnetic field solver for low frequency application. We have SI wave for simulation of chip and IC package. We also have iSpec for thermal to see the thermal of inside the electronic products. We also have MotorCAD, Ansys MotorCAD for simulating. This is a template based for simulating motors. We also have EMA 3D cable to simulate inside cable. We also have a Q3D extractor for RLGC parameter extraction. We also have a EMA 3D charge to simulate charges inside cables. And we have a no hertz filter. This for designing filter. Now we will be for today I'll be using Ansys HFSS to simulate the cross dipole antenna. So if you want to learn more about all this product, you can go through the Ansys website, which is ansys.com/product/electronics. And for today, we'll be using Ansys HFSS. What is HFSS? It means that HFSS means high frequency structure simulator. It is a general purpose for wave to the electromagnetic simulation tool for high frequency application. So some of the high frequency application, some of the example are antennas, microchips, filters, integrated circuit, PCB, RF components, and microwave components. And today we'll be do the cross dipole simulation under antennas, the principation of an antenna. And before we go through the demonstration on how to use the Ansys HFSS, this is some a little bit explanation what are the radiation field. So when a signal is transmitted from an antenna, it's radiate electro EM wave into the free space, and the radiation field are divided into two regions, which is the near field and the far field. So the near field will divided into two: the reactive and the radiative near field. So what are those? So for the reactive near field, this is where the in this region, the electric field and the magnetic field are 90 degrees out of phase with each other. Therefore, they are reactive. And to radiate or propagate the electric or magnetic field, it needs to be orthogonal or perpendicular with each other. And at the near field, there are the radiative field. This is where the EM field start to transition from reactive to radiating field. And what are the far field? The far field is the radiating field, where the electric and magnetic field are perpendicular to each other to the direction of propagation with the plane waves. So I'll be for the demonstration. We are going to import the cross dipole antenna from an existing file, and we want to. These are the picture of the antenna, the cross dipole antenna, and we'll be verifying the parameters of this antenna. So we will not be designing this because this is a already design antenna. And next, we need to set up the simulation for the near field line, and we set the near field radiation sphere. I'll go through more deeper during the demonstration. And finally, for the post processing, what we want to see is we want to plot the near electric field of the line that will be that we put during when we set up the near field line, and we want to plot the near field radiation pattern of the sphere that we already set up. So now I want to open the Ansys HFSS. So from my screen here, this is Ansys Electronic Desktop version 2024 R1. And as you can see, this is the dipole, the cross dipole antenna. And first of all, before we change things in the parameter or design, I want to copy this one first so that the original file doesn't get changed. So to copy this file, we simply drag this to the top here, and it will create a new design here. So we want to change this to demo. And save this. Okay, so when we make a change on this design, it will not change the initial one, the initial design. Okay, now first we want to verify that this is the parameter of this antenna. So we can see here under this properties, we can see the dimension, the dipole length is around 15 centimeters, with the antenna width around 0.34 centimeters, and the port gap width around 0.34 centimeters, and the frequency here, the lowest around 800 megahertz. So we want to see the port that we are already set up. So here are the two ports, port 1 and port 2 for antenna, the first dipole antenna and the second dipole antenna. And we can see the sources. You can see here it's around 1 volt with a 0 degree phase. And the second port is the same, 1 volt and 0 degree phase. And we want to see the analysis setup. So the frequency that we are using is around 0.92 gigahertz, around 920 megahertz. Okay. Now, before we go through, before we want to see the result first, I want to analyze this first. And so to analyze this, we simply right click on this analysis and click on analyze all. And it will take around less than 5 minutes for this to run. So we just wait and see. And if we can expand this result, we already have all the result for the return loss, all the far field, and some gain and a gain here. And so we don't need to add a result for the far field. We only want to see the result for the near field. So after we simulate this, I will go through how to get the near field radiation pattern. See here, this is the electric field, and I want to see it on top. Now you can see that the demo here, normal completion simulation. Now we want to see before we go to the near field pattern, we want to see the far field. You can see the far field gain here, X1. Yeah, these are the far field pattern for this cross dipole antenna. And to see this uh, inside the antenna, we can click here. We click on this. See the result will overlay on top of the design, on top of the antenna. And now we already have the far field. Now we want to see the near field pattern. So we simply want to first we want to create the radiation first. So we want to create the radiation line and the radiation sphere. So to do this, we basically want to draw a line on top of the uh, x-axis. So first we want to change the orientation to -y, I think. Okay, you can see here is the two poles here, in the center, and I want to draw a line outside the box here, outside the box. So firstly, we change the grid to XZ, and now we can draw anything on this XZ plane, and then I will be using this assertion. You want to create, yes, and we want to create a non-model object, and between things, okay, I think around here should be fine. And to see the line that we have created, you can take this, the point 1, and the coordinates is 25,015, and the endpoint, the point 2 is minus 25,015. Okay, so this is the line that we have created. Now we want to see, we want to create the radiation line. So to do that, we simply go to this radiation. Wait, before that, I want to rename this line to this body line. I want to change it to X line. Okay, now we go to this radiation, insert new field. Want to see the new field line and click, and we choose this line, the X line, and the number of points we want to change it to 101, and change the name to new field line 1. Then we click OK. Now you can see we have a radiation of the line. And next, you can see at this line, yeah, this is the new field radiation line. And we want to create a radiation sphere. So to do that, it's the same as want to insert a new field, and we click on this sphere. And for the perimeter of the sphere, we want it to be around 3-meter radius. And 3 meter, just and we want to start from 0 to 360 degree. The step of 2. And for the theta, this is for the phi. And for the theta, we want to start at 90, stop at 90 with 90 step size. And we simply click OK. You see here, the sphere and the line radiation are already created. And now to view the radiation pattern, firstly, we already create the radiation. Now we want to see the result. So simply we right click on this result. We click on create near field report, and we want to see the radiation pattern. And for the line, we want to see the line first. So we want to see the electric field at the line. So to see the electric field on the radiation line, we simply first we go to the create a near field report and click on rectangular report. And for the here we use the selective, and we use the geometry in the line. And we for the category the near electric, and we want to see the near electric total. And we simply click new report, and to share down the result. Here are the near field near electric field total here. These are the plot for the near electric field radiation. And next, we want to see the radiation pattern for the sphere. And to do that, we right click on this result. We click on the near field report. Instead of using the rectangular plot, we want to see the radiation pattern. So we click on this radiation pattern. And for the geometry, we want it to be the sphere. And for the primary sweep, we want the phi. And same, we want the near electric field and near electric total here. And we click on new report, and we can see here this is the the radiation pattern, the near field. So that simply is. And to view this on top of the antenna, we can right-click this and show in module window. And we simply go to this demo. And instead of orient, we want it to be on top here. And okay, there are two intersecting. This is because of the we on both for the far field and the near field. So you can basically you can view both at one time for the near field and for the far field. But if you want to only see one of so that you can compare and contrast. But if you want to only see one of these, so you can change the from this field overlays and we click part field and the radiation field. So we can see here we show the only the near electric plug two. So we click on apply. So now we can see only the electric the only the sphere the near field of the near field pattern. So that's how you do the simulation, and I think that's about it. Let me go back uh, to the slides, and that's how you see the radiation pattern. And uh, next slide is for the Q&A. Do you have any question regarding this demonstration? And if you have a question, you can unmute your mic or you can type it on the Teams on the chat box. And while waiting for question to come, I would like to review the conclusion during this webinar. So we already the summary of the linear objective. We already defined what is DFE and what is far field radiation. What is how to simulate we already know how to simulate the DFE radiation line and sphere using FHSS, and we already plot the near field radiation pattern using FHSS. And now I would like to pass the screen to Zulaika for further instruction. So Zulaika, you may take the screen.
Thank you very much, Mr. Farhan. Before we move to Q&A session, I already launched a poll. Please select the appropriate response and click submit. While we are waiting for your question, take a second to scan the QR code and follow on your favorite social platform. Stay tuned for all the latest updates and news. Does anyone have question regarding this topic? It seems that we might not have any question at the moment, but that's perfectly all right. Mr. Farhan, is there anything else you wanted to cover?
I think I already covered everything that I want to show during this presentation. And I think Zulaika, you can conclude this webinar if there is no question.
Great. Thank you, everyone. We appreciate you being here. We also encourage you to connect with us on social media to get the latest information. Don't forget that we will post our recording of this webinar at our YouTube channel. If you have additional questions, you may contact us by email or telephone. We are happy to provide additional support. Thank you all for attending. We hope you have learned and enjoyed this presentation. Have a nice day.
All right. Thank you, everyone.